All right. I think people are in. I think I will start. So thanks again for coming back. And I wanted to thank the organizers, which I forgot to do during my first lecture, but it's still graceful to do it at the last lecture, for organizing this. I have to say I've been thinking about these things for quite a while, based on conversations with Dan and Konstantin and Lexi and Anton Kapustin and Mike Friedman, a whole group of people. And I found it, a number of us, I think, found it very hard to really understand kind of the things people, someone that works in homotopy theory, I found it hard to understand all the things happening on the lattice model side. I found it hard to read the papers. I found it hard to understand what many of the words meant. And at one point around sometime in 2019 or 2020, Marcus Flum and Agnes Baudry and some others organized a conference at Boulder. And there was this, it wasn't really a secret talk, but it seemed like a secret talk. There was a talk that Daniel Spiegel gave at that explained all of this algebraic quantum field theory stuff in a way that was very understandable. And so many of us became secret fans of Daniel and watched that video. And Daniel was going through Peter Naikin's book. And I just, this conference is kind of a dream for me to get, I didn't get to meet Peter and Bruno and all those people, but to hear them speak about this stuff, these were the papers that finally made that material make sense to me, and I think for many of us. So special thanks to the organizers for pulling this group together. All right, so let me try. I have just a bunch of loose ends to, uh-oh, that's bad. Oh, well. Excuse me a sec. Let me see if they're getting back to life. Anyway, I've been fascinated by this, and I'm lecturing about this relationship that I learned from Alexi, that connecting things in certain kinds of lattice models. And so these are, I'm being, there's Alexi in one of his lectures talked about four different kinds. And it's not, anyway, many of these different flavors match up to something more. Let me just briefly call this topological side. I guess the quotes should go outside of topological. All right, on that side. And so there's many kinds of lattice models here. There's bosonic ones, there's ones with time reversal symmetry, there's gapped, there's topological. Alexi mentioned many flavors over here, and they align in various different ways with structures going on the topology side. And so here we have lattice models, and what do we have over on the topological side? Well, we have some objects of stable homotopy theory. And that corresponds on this side to invertible gapped lattice models. And there's this Kitaev spectrum, or this Kitaev homology that relates these. And this side, there's this conjecture. So it's conjecture that what corresponds to invertible phases on this side is this thing that has as a kind of complicated, it's a compounded symbol because it's built from, it's, as I said before, it's built from several different objects in homotopy theory. And we should probably give it a different name, just so that you aren't always just parsing the name when this when this gets put on the board. All right, and I think so. One of my goals in this talk was just to, I think these two sides influence each other. Certainly, you can do lots of things in homotopy theory, and it's only really when it comes in relation with another subject, like in this case, this kind of physics, that you get boundary conditions on your imagination, and you start and different structures kind of emerge as important, and it drives the development of other structures. And I think the same thing I'd like to say, that then some of the ways that gets organized in homotopy theory organizes an arena of questions over on the lattice model side. And my hope was in this series of talks to kind of give you a sense of this relationship. It's not very mathematically precise, but what one can do, even with just a metaphorical relationship, is look at structures that appear on this side and try to explain them on this side, or look for structures that appear on this side and try to explain them on this side. So some of the things that feed us questions in this direction are this idea of, first of all, there's reflection positivity. And that, in the invertible case, that was something Dan and I wrote a paper on, and in the not necessarily invertible case. So in the invertible case, I'll just put a check mark, like a mission accomplished check mark. That one, I think, is something that we've come to understand, but in the not necessarily invertible case, I didn't put the non-invertible case over here, but in that side, there's a lot of recent work that I described yesterday, and it's sort of all under this big project about dagger categories. And I was talking to Theo yesterday to get some of the latest. A lot of this stuff is not yet has not yet appeared, but this seems, at least from what Theo was telling me yesterday, to be quite well developed now. And I'll try to indicate in my talk today a little bit about what's driving us to find a structure here that gives us the topological model for reflection positivity. And the other thing, as I mentioned, was the emergent Lorentz invariance. And that's something, so I think we don't know on this side why that should emerge. And today I want to just kind of pose a problem purely on this side that I think might be related to ways of understanding that. So today I want to go more into the idea of some relationship, of thinking of this emergent Lorentz invariance as some kind of boundary condition, instead of just a declarative condition here, some kind of boundary condition on our imagination here, and to try to formulate just a question on this side, to formulate the issues that could give rise to Lorentz invariance on this side, and try to formulate some kind of a purely mathematical question. Okay, so that's one of my things for today. I didn't leave enough room, but there's an arrow in the other direction, and this stuff in homotopy theory we organize. So this is organized into a hierarchy or a spectrum level. It's organized, let me just say, into a hierarchy of infinity n categories via the cobordism hypothesis. So, and I also mentioned this a little bit at the very end of one of my talks, but I'd like to see, I mean, I think in homotopy theory, we don't really think of these as separate packages. We can work in stable homotopy and bring about bring to bear all of our powerful computational tools, but this doesn't really look meaningful, even if we're only interested in the invertible case. It doesn't look really relevant to the structure on this side if we merely isolate to spectra. So the spectra emerge as the invertible parts of these infinity n categories, and there's really a much richer structure here. And it's very natural to ask that this Alexey's theorem, or this, I don't know the status of this as a theorem, but this Kitaev homology spectrum, the fact that this is an infinite loop space, I also mentioned this last time, it seems like that should be the invertible part of some hierarchy of infinity n categories, and that there's really a more categorified version of this infinite loop space theorem. But I don't know if that's plausible from the point of view of lattice models. Let me just think if there's one thing else I wanted to say. Yeah, I think, oh yeah, okay. So that's one way of inspiring a series of questions. Then what other value is there in having this relationship? Well, as I said, it inspires the development of structures on the math side, and it also kind of reins in some of the many possibilities of things we could just make up. And on this side, we have extraordinary computational power, and on this side we could attempt to you can imagine that this works and go and make a computation here, and then that makes you go back to this side and look for some invariant structure that exists on the lattice model side. So those might just be numerical invariants. We might say the phases are classified by some element in Z mod 2 or by some kind of category or something like that. And on this side, you might want to look for how to make those invariants. And there's a lot of existing invariants here, which one can hope to explain on the homotopy theoretic side. So one of the things I've been excited about at this meeting is that on this side, we know when you have a three-dimensional topological field theory with certain structure, you associated the value on a circle is I'm blanking on the name. It's this braided-monoidal category of having a senior moment. What do you? No, it's these excited states. No, one more guess. No, it's what Peter's been lecturing about. The super selection sector. Yeah, this braided-monoidal category of super selection sectors coming out of the. So that's something I think that's predicted in a way by the way this gets organized, or in some sense it's predicted by the way this gets organized on the right-hand side, and you can try to get that out of a system. Okay, so that's just kind of recapping sort of the things I sort of see about this relationship, and I wanted to just go back and refine one thing that I said yesterday. So, okay, so yesterday I kind of brought up the question of starting with something on the topological side and trying to produce some kind of lattice model. And that was meant as a way of looking for obstructions to emergent Lorentz invariants. So So let me just redraw a picture with a little bit more care. So on the topology side, I'm going to look at sigma 2 IZ M spin, and then I have a map from that. I have a map from that to sorry. Just sigma 2 IZ. So these are meant to classify invertible phases for framed theories, framed manifolds. And these are supposed to be, or these are just invertible phases, and these are supposed to be spin invariant invertible phases. And now let me just write down the sequence of homotopy groups. So I'm going to look at pi 0. Just I'm going to look at pi. I think I want to look at.
The M spin is still supposed to be like an upper.
Oh, I'm sorry. It's an upper M spin. I'm very sorry. Thanks. Yeah. It's meant to be a function space into it. And then I'm going to just write down the homotopy groups. And so they're indexed kind of funny. So this starts out as 0, Z0, Z2, Z mod 2, Z 0, 0, 0, Z. This looks like the K theory groups up until about this spot. There's another Z down there, but I won't draw it. And then on this side, I get Z0, Z2, Z2, Z mod 24, and then 0, 0, Z mod 2, Z mod 240. And there's a map between these, it's the obvious surjective maps. So these groups classify invertible phases on, and I'll just say what are on the Euclidean space. So this is on R0, this is on R1, on R2, R3, R4, R5, and R6. And so the invertible phases are the invertible lattice systems like on R1 are two-dimensional theories. And on R0, they're one-dimensional theories. And the one way to read this is to, if I want to look at the situation on R0, I have to know when I look at this that this is a model for the category of superlines. And then I would know that to that I got something like a vector space. And as I mentioned last time, one way to try to understand spin invariance is to try to start from something on this side and try to make a lattice model. So the lattice models are supposed to, by emergent spin invariance, they're supposed to come from here. And if you can find something down here, if you can make a lattice model for something down here that doesn't come from there, then you've got a contradiction. And if you attempt to do it and there's an actual mathematical reason you can't do it, then you know someplace, then you have an idea of the things that might contribute to spin invariance. So I just wanted to look at this table because last time I focused on this. Okay, so there's a Z2 invariant of just invertible phases, not necessarily spin invariant ones on R5 or a six-dimensional theory. That's this Cavere invariant theory, this Cavere invariant, and there isn't a theory here. And so one way to approach this is to try and build a lattice model that's detected that comes from that theory, from that invariant. But there's another difference, which is right here. And And that one's more subtle. That should be accessible already in dimension 2. But this says, in this case, we have a theory, which we can certainly write down. And I think Alexei's maybe mentioned some models like this. You can get this from a free fermion theory, but 24 copies of it can be moved into the trivial phase if you don't assume spin invariance. And then, so that must, if there really is an emergent spin symmetry, there must be something that stops you from moving 24 of those to the trivial phase with local operators under the assumptions that we make when we're defining whatever we mean by lattice models. So I will confess I have a very poor understanding of that situation. And so there is an opportunity to try to test the Lorentz invariance here. My understanding, though, is that it passes that test, and this is not really the first place you can look for an obstruction.
My question.
Yeah.
So the last line, this on the left, shouldn't it be Z plus Z?
On the last line, sorry, I can't hear very well.
Plus Z, yeah.
The left
Oh, it's
column.
Z plus Z. Yeah, sorry. Yeah. Yeah, that's right. So this is one of these invariants is the index of the Dirac operator, and the other, as I mentioned last time, is the Dirac operator coupled to the with coefficients in the tangent bundle. Okay, so after all that preamble, I want to say something about the problem of starting with an invertible phase and building a lattice model out of it. So where's Dan's, where's the Hutterino? All right, so how am I going to go from a phase, so something in topology, so a topological field theory, how am I going to go and get some sort of lattice model? Well, so the lattice models, they're ultimately built out of, you have a bunch of points somewhere, and you need to get a Hilbert space over each of these points. So maybe these have a lattice index, and you're supposed to find some Hilbert space HL. So a topological quantum field theory, it has a lot of information, but it only evaluates to a vector space up one dimension below the top. So suppose Z is an n+1 dimensional topological quantum field theory, then Z of a closed n manifold, that's vector space. And so, I'm sorry?
Doesn't matter what target kind of.
Oh, sorry. Now I'm imagining that I'm imagining that I'm moving from this kind of system. So I'm looking at the universal target category. So this would be really a super vector space. There's, as I mentioned last time, this hierarchy of universal target categories. So we have the universal target categories I was indexing like this. So the one for 0-dimensional field theories was, or let me just think. So that's just supposed to be the complex numbers. The one for 1-dimensional field theories is super vector spaces. And then there's a procedure. And I mentioned the names last time, Theo and David, and then Tomer, Lior, and Shachar. have sort of, there's a procedure for producing, starting with one of these, producing the next universal target whose invertible part is this. So in principle, I don't need to tell you what these are because you can just describe them, but this one turns out to be the equivalent to the sort of the Morita category of super algebras. And then it goes on down. These are some kind of fusion categories, and it just continues. It continues down. Or these are, or maybe it's better to say these are linear categories over supervector spaces. But I don't, in this hierarchy of structure, I see numbers here when I'm looking at an n manifold, and when I'm looking at in codimension 1, I see a vector space. So the only way I can get a vector space that's floating around is by somehow by making a little neighborhood of what I'm looking at of this point evaluate in the field theory to a closed an n, the same thing a closed n manifold does.
Is the TQFTZ that you're considering an invertible field theory, or are you thinking more general?
Right now, I'm just thinking more generally. Yeah. I'll try to do some examples of both kinds if there's time, but I'm just imagining the problem of taking something arbitrary here and going back to a TQFT, and maybe at some point I'd have to imagine it's linear. And I should have said before I even started this that this process is pretty well developed by Dan and Constantine, and I have, and so this is just kind of my way of trying to explain some of their ideas. All right, so that's one idea, that somehow I have to do something around each of these points and get them to evaluate to a vector space. Now, I said, and in fact, just to keep things simple, I'm going to ignore the super part right now and just to keep the discussion a little simpler. So I'm just trying to get a complex vector space. And then I'm going to want to do things to these vector spaces. Then I somehow need to, so I need to somehow make a point look like a closed n manifold, and then I need to find a Hamiltonian. And the ground state, so I still don't know anything, but I do know that the other thing I know is the ground state of that Hamiltonian is supposed to have to do with a different vector space, a closed associated to some other closed manifold. Like if these are on the sphere, maybe I'm trying to calculate the vector space associated to the sphere. So already there's a difference, right? This merely produced a vector space, and it was not a Hilbert space. So that already sets up a difficulty that we would only now know how to deal with in the reflection positive, in the invertible case. And so in this fantasy of how we might construct a lattice model, I need to somehow assume that this dagger category stuff is up to this job, and I believe I'm told that it is. But so already this isn't quite this category. It has this. It's some incarnation over here of something that remembers reflection positivity. But so this is, I'm going to bring this point up in several places because it's always kind of bothered me that we do things and then we just say, oh, and there's a Hilbert space structure on them. But so I'll do some examples in just a second. Okay, so how could I get a vector space out of something, out of sort of the neighborhood of, oh, yeah, sorry, I wanted to say something else. I wanted to say something else that we're gonna kind of look for. So in the models that we've been told about, that the people always work with, like the Majorana chain or the AKLT model or the toric code, it's not, they don't, I mean, we have to describe them in a finite amount of time. So there's some system on all of R or the plane, but we don't, they're not really, there really is just a small instruction set. There's a little instruction set for writing down each of the Hilbert spaces, and then a little instruction set for taking just a couple of them nearby each other and writing down the Hamiltonian. And we just use that little instruction set over and over and over. And in a sense, these topological field theories, there's something very finite about them, and we're gonna look for a little instruction set that's just a finite amount of data, and we'll just kind of keep reusing that little instruction set everywhere to make a topological field theory. So we're going to produce only, I mean, a lattice model. So it's only going to produce very special kinds of lattice models. And one of the features that they have is that they are fixed points. There's a way to renormalize them, and they're always fixed points under, or they tend to come to you as fixed points under renormalization. So, okay. All right, so after all of that, let me just try and say something about this. So let's work. Let me work at this level. So suppose I'm looking at a quantum wire or a two-dimensional theory, and I have a bunch of points on the wire. And I want to do something that makes these evaluate to a vector space. So a vector space, so that's a, yeah, I have some, let's say I have some algebra in mind, and I want to imagine, I want to do something at these points so that they each evaluate to a vector space. So over in this, so this category, as I've described it, is the Morita category of algebras. And so, so I should really imagine, I really should have, I think maybe I should have said something different here. I want to just temporarily replace this by the two category of categories enriched over supervector spaces, and functors that preserve that enrichment and have preserved co-limits and a bunch of things like that. So left exact functors of this kind of category. So I have some category like that, and what I really want is a vector space. So where can I go to write this? All right, what I really want is to evaluate a vector space, and so I have to, so let's take my category. Now, how do I find vector spaces in here? Well, among these categories is so this is a symmetric monoidal category. Among these is the tensor unit, which is just the category of supervector spaces itself, and functors in C2 from this to itself. Well, an additive functor from supervector spaces to itself is just given by where the trivial, the one-dimensional one goes, and that's going to be just some supervector space. So the typical object in there is itself a supervector space. So I could start with some random one of these C's in this C2. And one way of getting a vector space, of at least touching vector spaces, is to write down some kind of a functor to the tensor unit. And then now everything in this world has adjoints, so that functor will have an adjoint. Let's see, maybe I'll call this one D. Just a sec. I'm gonna get, there's a right place to put this, and I'm probably doing it wrong, but this means it's left, say the left adjoint of this. Okay, so this composite data produces for me a vector space A. And then the fact that these are adjoint functors, so that gives me a map from D star. That makes this composition into a monad. Just the fact that they're adjoints, and that corresponds to a map from A, tensor A, into A, making A an algebra. And then, in fact, that condition allows me to identify C with the category of left A modules. So sometimes it's nice to just start and think it's the category of algebras and it's the Morita category of algebras, but the structure I want to emphasize comes from remembering that you've chosen this condition. So in the language of topological field theories, this is a boundary condition for the theory. Now, even if I was interested in an invertible field theory, like say one coming from an invertible algebra, so like the field theory coming from Clifford 1 is the Majorana chain is the non-trivial phase of the Majorana chain. That even if I'm interested in that, this boundary condition is not an invertible morphism. This is not a Morita equivalence of this with the trivial algebra. So when I'm talking about something being a category of algebras, or when I'm trying to get a vector space out of an object here, like the underlying vector space of the algebra, I have in mind bringing into the game boundary conditions that aren't invertible. So that's a reason, if you're just thinking about this problem of going back to lattice models, you don't want to stay just in the invertible. You need to think about the rest of this category, even if you're ultimately only interested in the invertible part of it. So it's another reason that I'd like to see if Alexi's conjectures can be generalized, can be kind of brought into this more categorified context. Okay, so that's something called a boundary condition, and if I put a boundary condition, so the usual way to draw this is to have, so there's a whole story of the cobordism hypothesis with singularities, and there's a whole story about boundary conditions, and I don't think I've left myself enough time to really carefully explain that. But there's pictures that you draw when you draw a theory with the boundary condition. So this kind of, maybe a dot like this I'll think of as corresponding to some a zero manifold, right? So you can think of these as, you can think of a field theory with a boundary condition. That's also a functor out of some kind of Bordism category. And so in that case, you have a zero manifold, and then you have a part of the boundary labeled by your boundary condition. So you think of this, so this kind of manifold in your field theory, if you want to talk about a boundary condition, you're allowed to color parts of the boundary of the manifold. So I can think of this as going, this might be my D, and my D star might be this. And so this picture here gives me my, this picture evaluates to a vector space, and it gives me a picture of my algebra. And the fact that it's an algebra, I mean, I think this story is very old. I mean, these kind of pictures and this kind of story predates the proof of the cobordism hypothesis. But this cobordism will give me the multiplication on the algebra, et cetera. Okay, so if what I'm doing then is I'm surrounding each one of these points by a boundary condition. All right. And now out of the topological field theory, I could stick in this cobordism here. So I can go down. And I could go down from all of these. I want to draw this differently. Okay, I'm going to do something with these boundary conditions to get them down to a picture like this. So out of the language of topological field theories, I can write down this operator from the tensor product of all these vector spaces down to this one. And then if I wanted to, I could go back to the original picture. Now, I'm not explaining this. I'm not giving you very many details here. And so that gives me at least some kind of operator from a tensor product of these vector spaces down to another tensor product. And that operator corresponds to projecting to the ground state and then going in by the adjoint of that. That's not the Hamiltonian. So that's another thing that topologically you have access to the ground state. But if I wanted to write down the Hamiltonian, what I produce, the tiny instruction set I produce out of this is this picture. Okay, so so this just corresponds to the multiplication map from the algebra tensor itself to itself. And if I compose with this, I get a map from A tensor A to A tensor A that's trying to be the projection to the ground state. And if I want to write down the Hamiltonian, I have to take 1 minus that, because the ground, what I really want is the projection operator to the orthogonal complement to the ground state. And then those give me, that gives me some local projection Hamiltonians. And from this system, you can write down a frustration-free Hamiltonian. So I want to just indicate what happens in higher dimensions. But maybe I'll just say one thing about this without going into details, because I think it's also important. If you wanted to do this for the AKLT model, you just take the algebra of 2 by 2 matrices, and you look at the under matrix multiplication. And so that's not quite the AKLT model. The AKLT model had a 3-dimensional vector space at every site, and you either have to renormalize it once to get 4-dimensional, or you take the you remember this SU2 action, and you split off the spin doublet part of the 2x2 matrices. And so you can write down this model, and it gives you all, it's the AKLT Hamiltonian, and you write down the AKLT model, but you completely, if you're doing this from the point of view of topology, you completely lose one of the main features of that AKLT paper, which is to compute the correlations between the ground states. So again, the correlations between the ground states depend on the Hilbert space structure, and without having this dagger stuff work in the not invertible case, we don't have access to the Hilbert space structure, and so we can't. The topological field theory can't access sort of specific information about the correlation functions, but presumably it can asymptotically. All right, gosh, I'm really going slow today. So maybe what I want to say a little bit about what is supposed to happen with this picture when you do it in higher dimensions. And it's a little easier if I start if I try to think about if instead of doing it with vector spaces, I do it up at the top dimension where I'm evaluating to numbers. All right, so I want to so let me just do an example. I'm just going to run through an example of a two-dimensional unoriented theory. And I'm going to work, and I want to sort of evaluate. So the question is, how do you evaluate? How do you evaluate the number you get? So I want the number, or if this is like a stat mech model, I want the number analog of a Hamiltonian lattice model. So how do you compute the number? And the answer is going to be, it's a contraction of a tensor network. So I have to say a brief word. We all know, so we know what tensors are it's just some numbers. You have several indices that might range from 1 to n, and you put some down and you put some up. And this thing, once you specify what index you had is supposed to evaluate to a number, and then you can contract you might, if I had some other tensor like this, I can contract two indices by, say, summing these over L, and I'd get some summing over the common indices, and then I get some new tensor that might be R, I, J, L primed, K, and I get some new tensor. Or I could contract, I could take a tensor like this. And I could contract those into and get something of the same sign or side, or I can contract all the indices and just get a number. So there's a graphical notation for tensors that I'm sure people are familiar with, that was introduced by Roger Penrose when he was I know this because Roger told me, and this was introduced by Roger Penrose when he was a student of Hodge and couldn't understand these complicated symbols. And that graphical notation has been revisited and revisited, and really in the early days of writing down three-dimensional topological quantum field theories, they were not, this led to the formulation of the cobordism hypothesis. They were all written down as tensors. as tensor diagrams or string diagrams or string net diagrams or whatever the diagram calculus is called. So I'll just imagine, so the graphical picture is that you have some dot that represents your tensor, and then you have things that are either inputs or outputs. And these represent, these are correspond to these positions, and they might have several labels. And then you can contract tensors as long as they line up like that. I can contract these two, and I get a new tensor that kind of skips those. Right, so when I contract these, I'd get a tensor that takes all these inputs and that now only has these inputs. Shoot. Okay, so I think I'm just going to give have to let me just think for a sec. So all right, so what I want to do is start with this unoriented theory. Okay, so my two-dimensional unoriented theory so that's supposed to correspond. I'm gonna be over the real numbers, and it's going to correspond to the quaternions, so H modules. And in order to give it the structure of being unoriented, I have to pick some data, and that data has an expression in terms of a tensor. So, so the first thing I want to say is I'm gonna so my labels are going to be, I'm going to choose a basis for the quaternion. So the labels will correspond to 1i, j, and k. I could label those by that. And so usually, so you also have to have an orientation on the boundary. So if it's unoriented, I get to flip things, and I have these orientations near each of the edges. Okay, so this is going to evaluate to some number, but I also, since it's unoriented, I have to tell you what's happening at that if I've labeled this, say, with I, how do I flip this? How can I flip this one out? I'm going to keep the same orientation. So to replace this by this, you have to choose an isomorphism. You have to choose an an H bimodule isomorphism of H with its dual. And there's a unique one up to a real scalar that sends 1 to some multiple of the dual of 1. I think I'm not going to have time to go through this whole example. I'm just going to, without much. All right, let me I'm just gonna say something. What's that?
Let's just see how we get with it.
Yeah, all right. Instead of worrying about it, yeah. Yeah, okay. Yes, indeed, right. So the other thing I need to do is to be able to flip the direction or flip this without doing that. So let's take this one, and I want to flip the direction. And that's going to correspond to choosing an algebra isomorphism of H with the opposite. Technically, it's just a bimodule, but I'm gonna I'll choose this isomorphism. Okay, and so then the rules. So then let me just try and So the rules are, you take a manifold. So I'm going to let's take RP2. Okay, and I want to triangulate it. So the easiest way to triangulate RP2 is to draw a picture of a icosahedron that's not really going to be right done. Octagon. So that, if I glue those edges together and then I get that, that gives me a picture of that gives me a picture of that gives me a triangulation of the real projective plane. So now what you do is you start and you draw a small disk around each of the vertices. So this is a disk because of the edge identifications. All right, and now I want each of these to evaluate to a number. So I have to choose boundary conditions. In the language of in the language of field theories, I'm choosing a boundary condition here and a domain wall there between the boundary conditions. So each one of these little dots turns into some kind of turns into a tensor. It turns into something. So I've labeled. So this. So each of these green things, it corresponds to my choice of quaternions. And this thing here corresponds to a bimodule map from the quaternions to itself. I'm doing something wrong. I'm sorry, it corresponds to a left module map. Okay, so at these edges, so now I have to tell you a few things. I have to decide whether these are outgoing or incoming. And I have to tell you the direction that I'm traveling. So the way this works, so this is now a defect between these, or a domain wall between these boundary conditions, and it's a left bimodule map. So the left bimodule maps is just isomorphic to H. So each of these, so I want to think I've created a little tensor network here. Each of these things can be labeled 1, I, J, or K. And then to get a number out of that, I multiply them together as I go around this circle. That gives me an element in H. I have an isomorphism of H with H dual, so I can pair against 1. And then this product, once I've labeled each of these, it evaluates to a number. All right, now I want to try to end somewhere close to on time. So so each of these evaluates to a number. If I was doing this one dimension lower, each of those would evaluate to a vector space. I'm kind of imagining I might be taking the product of those numbers. In vector spaces, I'd be taking the tensor product of those. But now I want to contract this tensor network along all the indices. So if I'm here, let's suppose I want to contract these two indices. I have to change. So I have a single object that I'm sticking in everywhere. This is a bad, I have to change this picture to something outgoing and make sure these line up. And then I can do the tensor contraction. And what that corresponds to in boundary conditions is this thing that is called condensation in this collaboration, and it writes the identity as a sum of map to the vacuum and a map back. So once I tensor contract, when I tensor contract, geometrically, what that does is it does surgery along this edge, which was in between, and I get this. All right, and now you can calculate this number, and you do surgery along. So you go ahead and you do surgery along all of these things. That's just graphically, that's just representing you're actually calculating the contractions in a tensor network, but graphically, geometrically, you're doing this surgery, and now you're calculating the number associated after you've done all those surgeries. This number associated to the this little two manifold with this boundary. Then there's another step where you have to do surgery on these and fill those in, and then that calculates the number on RP2. And with this particular choice, if you do this on any surface, with the appropriate choices, I think you get suitably normalized, you get something like negative lambda to the Euler characteristic of the surface. And reflection positivity makes this lambda have to be plus or minus 1. And so with suitable choices, you get, you can calculate that this is -1 on the real projective plane. So you're supposed to imagine that there's a version of this one dimension lower that's evaluating the vector spaces. I just wanted, I'm sorry, this is not, just want to say something very quickly if I can. If I was in a higher dimension, so maybe I've got a 3-dimensional lattice, then I'm gonna surround each of these with a disk, and I have to have, so now what that's gonna give me when I intersect that is some disks with a spherical polygon drawn on them where it intersected all the appropriate, it intersected all the appropriate edges. Sorry, something like that. And each of these faces gets labeled with a boundary condition. Each of these edges gets labeled with a domain, a defect between, a domain wall between them. And each of these vertices is labeled with a defect between those domain walls. And so now I'm, in a way I haven't explained, this is data you have to be able to choose out of your topological quantum field theory, and then this thing will evaluate to a number or a vector space if I'm looking one dimension up. And this gives me some kind of tensor network of those, something I can interpret as a tensor network of those operators. And I wanted to, let me move this point over slightly, and I just want to tell you what's happening here. If I have another one of these over here, and I contract these tensors, that will perform, what that will do is that will do surgery on this. and it will remove these defects and line up these blue ones. And topologically, what you're doing is you're writing down, you're starting with this lattice, and then you're building a handle body decomposition of the manifold. And at every step, you're interpreting, you're building up the value of the ground state or the value of the stat mech model through what you want to interpret as tensor contractions as you do each surgery step. So, all right, I'm sorry, that was a very sketchy, literally explanation. But the upshot of this is that you can, what it looks like is that you can build lattice models or stat mech models, provided you have enough boundary conditions of certain kinds. And so that's one place that seems like it's the only real obstruction from the topological picture, the field theory picture, to getting back to the lattice model picture. And so it raises a question on the topology side, which is does the existence of enough boundary conditions guarantee sort of the emergent spin invariance? Boundary conditions plus the Hermitian metric. So that's something I've been puzzled about for a long time, and I think we're starting to have an apparatus of definitions where that's actually an actual math question. All right, I'm sorry I went over again. I think I'll stop there.